Welcome back. This is example 4 of Z-transform. In this example, the input is a complex exponential and we are asked to find yn. In particular, the complex exponential exists for all time from -infinity to infinity. So this is different from previous example where we are considering only causal signals. In particular, we say that the input signal xn is represented by a complex number z0, and this z0 will change with n, the time index. So when n is equals to 0, z0 to the power of 0 is 1, and when n equals to 1, it will be z0, and when n equals to 2, it will be z0 times z0, and so on and so forth. In this example, we are considering for n equals to -infinity to +infinity index. Now, we know that for discrete time linear time invariant system, if we are given the impulse, then the output is simply the convolution of the impulse response and the input. We can substitute xn as z0n in our example. So if xn equals to z0 to the power of n, therefore x of n minus k is z0 to the power of n minus k. We can then substitute this value into the convolution equation, and let us now see what happens. The convolution equation from this point becomes this equation, and we know that we can break z0 n minus k to be z0 to the power of n times z0 to the power of minus k. Now, since this summation is over k, we can move z0 to the power of n outside, leaving us with this expression here. And this expression, of course, is the Z-transform, the bilateral Z-transform of hk. And if this sum converges, then let us call this h of z0, where h represents the transfer function evaluated with z equals to z0. This would be a complex number, and this complex number modifies the original input of z0 to the power of n by an amplitude as well as a phase. Now, remember that we are evaluating this convolution with an everlasting input x of n. Therefore, the y of n that is generated is the steady state response. There is no more transient left. Now, what we find is h of z0 is a complex number that tells us how the magnitude and phase of the input signal will change, and we realize that it is the same z0 to the power of n, the same input, but its magnitude and its phase will change. We call such a function being processed with, that means the real signal amplitude and phase change, but its frequency didn't change. We call such a signal an eigenfunction. So what we have realized now is that the complex exponential is an eigenfunction of a discrete time linear time invariant system. And it is also the same reason why cosines and sines are, because cosines and sine simply are sum of two complex exponential. The next page shows what I'm talking about. If we have an eigenfunction called xn, then the output is the same xn, except that it is being multiplied by, in our example, a complex number, and this complex number will change the amplitude as well as the phase of the sequence x of n. When x of n is the complex exponential, it is a real and imaginary for every term x of n. So let's have this example where our complex exponential has amplitude a, a frequency omega naught, and its initial phase. Then what will happen to y is that the magnitude will be changed from A to A prime, and its phase will be changed to phi prime, where phi prime is phi plus whatever new phase that it has encountered. So h of naught, this value here, is actually a complex number with a magnitude for the gain and a new phase that will be introduced to the original system, or sorry, to the original input signal. Later, when you study Fourier transform, the h, which is now called the transfer function, will be replaced by h omega, which is called the frequency response. The frequency response can be derived from the transfer function by substituting different z's, but in this case only for frequencies. It will tell us how the frequencies of different eigenfunctions will be affected by its magnitude and phase when it pass through the LTI system. In the next slide, I will show you an example. In this example, we are given the transfer function first. We are also given an input, which is a complex exponential. It is rotating at 0.2 pi radian per sample, and it is a decaying exponential because this is 0.9 to the power of n. If you prefer to visualize the complex exponential as cosine plus j sine, then this is the same, but we do not need to do that. Actually, it is preferred that you work in the polar notation of 0.9 or complex exponential notation in this way. Now, how do we work on this problem is this. We identify the frequency omega naught. The input signal omega naught is 0.2 pi. We substitute this value as j 0.2 pi for z. So it's simply z equals to 0 plus j 0.2 pi. I made a mistake. In this particular case, because the input is the entire signal, so this is z to the power n, z naught to the power n, we should substitute this entire value as z here to get the frequency response of this particular z. So we substitute here at the bottom, and basically this is the z. So if you look at the equation on top, z squared, so this is z again to the power squared, and so on. So we are working with this transfer function with z is equals to 0.9 ej 0.2 pi, and we get a complex number out. Typically, we don't like the number to be in rectangle form. We want it in polar form because it will tell us the magnitude that we introduce to the signal as well as the phase. We take this magnitude and phase and multiply it by the original signal. So this is z naught to the power of n. His magnitude will be changed by this, and his phase will be changed by this. This is the final answer. The magnitude, the gain at this frequency is 4.7 multiplied by the original signal here, and a phase shift is introduced to the output. So this is the example of how we find the discrete time system affecting a complex exponential. Thank you.